Hello, my name is Jan. I'm from Socialbakers, and this evening I'm going to talk about sentiment analysis on social media. Sorry. Yeah, so Socialbakers is quite a large company. We have over 500 employees. More than 100 of these employees are engineers, like developers and so on. And 42 of these employees are data-related guys. They are data engineers, data analysts, researchers, and so on. We have offices all around the world, but most of the engineering is placed in Prague, Pilsen, and Brno. So even though we have coverage of the globe, the most interesting things are developed in Czech Republic. We have a lot of customers, like 2,500 or more. And as you already heard, they are pretty well known. They are customers like Jägermeister, for example. Recently, we celebrated 10 years, so we are not that new on the market. And even more recently, we got acquired by Astute, which is an American-based company. So the introduction I just gave you is not proper because this acquisition is pretty fresh. And I only have numbers for Socialbakers. I don't know how many employees we have right now and where we are. So from the Socialbakers point of view, what we do, we help marketers on social media to do their work better using some AI or some very useful tools. We don't have just one product. We call the product Socialbakers Suite, but in fact, it's not one product. We have like 5 or 10 different products. We help marketers with some kind of inspiration. We recommend them content if they need to. We have one of the largest database of influencers in the market. We provide some analytics of social media, profiles, followers, and so on. And we also help people to communicate on social media via some channels and via our application. As I said, we have a lot of products under one roof, and clients all the time hungry for new features, which means we have pretty interesting job. We can work with a lot of different data. We can work on many different problems, and we can choose a lot of different approaches thanks to this. Because we work on natural language processing, we do some computer vision, we even do some like time predictions. We predict if content will be successful or not, for example. I'm from innovations team, which is one of the data teams we have in the company. This team has 7+ researchers. We have someone new in the pipeline all the time. And we all enjoy this variability. As I said, we work, for example, NLP and computer vision. We work on one problem for a few months, and then we just change, let's say, product team, very small product team, and start working on something new in completely new domain. So for example, what I'm going to talk about today is the sentiment analysis. There were in total 3 researchers working on the problem, but we never worked in more than 2 researchers team at one time. We, let's say, rotate researchers between projects. So these are the guys who are working on the problem of sentiment analysis on social media. So in our case, sentiment analysis is an automated process of recognition of how an audience feels towards any given subject from written or spoken language. Specifically in our case, it's just written language. We don't process sound yet. We may start do it in the future, but we don't do it yet. And you can see some examples of written text of messages we process at the bottom of the slide. To simplify what I just said, we do some kind of text classification. We classify texts into 3 classes: positive, neutral, and negative. And for example, the first message, OMG, worst day ever, should be classified as negative. the message at the bottom, "You're welcome," should be neutral, and "lol, you make my day" should be positive. What we don't do right now is considering context of the messages. If you read them from the top to the bottom, "worst day ever," "lol, you make my day," "you're welcome," the last two messages don't sound that positive and neutral. They are rather sarcastic. That's something we don't analyze right now, the context. So we analyze individual messages. From the client's point of view, there are a number of use cases. For example, clients run some campaign on social media, and they would like to know if comments of users on the campaign post are positive or negative, if they like it or not. Because by default, you typically have only positive feedback available on social media. You can give a like, but not don't like. Another use case is that when clients communicate via direct messages with users, some users are not happy, so they may have some complaints. We can analyze the stream of messages, analyze or identify the negative ones, and route those negative messages to specialized teams that can handle such cases. So we can analyze the messages, the conversations, and redirect them to specific teams. Another use case, we can, for example, monitor sentiment towards specific topics trending on social media. We can pick some, I don't know, actor or politician and monitor if people like him or not from messages. There were also some internal motivations, so not based on feedback from clients. The first one is that we thought it would be very nice building block for much more complex solutions to have the sentiment. For example, you can imagine if we develop anomaly detection, we can detect if, for example, traffic on your profile is larger than it should be. It would be nice to connect this with the sentiment analysis, so you know if it's positive or negative change for you. And another motivation, we found out from databases that some clients tried to do sentiment analysis by hand anyway. We provide them, or we provide clients with labels. They can define their labels and label their content and filter it and work with it as they need to. And we found out that some of these labels were named positive, neutral, negative. So they were trying to do it. We made a quick analysis and we found out that if it would cost $5 per hour to employ someone to label a sentiment, and if that person could label 100 messages per hour, large portion of our clients would need $10,000 to $100,000 every month to pay these people to label the sentiment. So theoretically, it was just very rough analysis, but theoretically, providing our clients with the sentiment could be beneficial for them. And here's another example of how we could use, or how we use internally the sentiment. One of the teams called DAT, Data Analysis Team, created this report, like, I don't know which year, maybe last year. They just analyzed comments and messages on Game of Thrones profile on Facebook. And they did it before and after premiere of each episode of the last season. And you can see pretty nice result. When it started, most of the messages were neutral. People didn't know what to expect. And after the first 3 episodes, they started to be pretty negative. And that's approximately what I remember from that time. When the last season was ending, people were very unhappy with the ending. They wanted the authors to reshoot part of the series or a few of those episodes. Okay, so we have a reason to create solution for sentiment analysis on social media. The primary purpose of the team where I work, the innovations team, is not to do machine learning. It's to solve problems. So our very first work wasn't to develop solution, but to find some existing solution, something that would solve the problem, and we could invest our time into something that can be solved that easily. We had some requirements. We wanted to be able to process 50 million to 150 million texts every day. We wanted something that would be able to recognize and analyze 5 to 10 different languages, including Czech and Arabic. And we wanted a solution that works very well on social media, which is not standard because social media texts are not something what you typically analyze with natural language processing algorithms. These texts are very short. They contain a lot of slang. They contain a lot of emojis, and they are very diverse. Like, there are many different topics people are discussing. For the purpose of evaluation, we created a data set of 500 hand-labeled Facebook messages. We labeled these messages in the research team, and we created it in such a way that it was balanced. So we have the same amount of neutral messages, negative messages, and positive messages. And we call this data set a benchmark data set. So we researched available services and libraries and so on. We ended up with 13 different options. And from these 13, we picked 2, from our point, best candidates. The first one was Amazon Comprehend. It worked pretty well. It supported a number of languages. It didn't support Czech or Arabic, but like 6 or 8 different languages in that time. But we estimated the cost to $37,000 every month, which is quite expensive for, let's say, in this phase, just experiment. It was expensive. The other option was Vader Sentiment. It's a library, it's open source, it's rule-based, but unfortunately, it contains a lot of, let's say, linguistic rules, and we would need a linguist to understand the rules and update, for example, the library, which is really bad drawback. Another thing is that this library is only in English. We were thinking about an option to translate all texts into English and then send it into Vader. But again, we estimated cost almost $30,000 a month, which is a lot. So at the end, we decided to use the Vader as the very first baseline, but we knew it's very, very short-term solution. First, it's only English. Second, we can't update it. What we also got from this initial research is this benchmark. If you look at the chart, the first 3 columns are accuracies on the benchmark set for 3 candidates we were choosing from. The last column is something called inter-annotator agreement. If you ask 3 people to label sentiment on some texts, how frequently it happens that they agree. So on average, which accuracy they achieve. And we know that it's approximately 80%. So 80% accuracy is human level performance. This is, let's say, the best we can expect from the solution we are going to create because we learn from people. And the bottom red line, you can see having approximately 33% accuracy. That's basically a random prediction of the 3 labels on balanced data set. So if we would have something that just randomly predicts some labels, we would achieve 33% accuracy. If we would let people to do the job, we would achieve 80% accuracy, and the machine learning solution should be somewhere in between. And based on what competitors can do, we picked 65% accuracy as our target. That's something we would like to achieve. So we delivered the baseline, and at the same moment, we started to work on in-house proof of concept, our own solution. We started to work on the project in 2018. Since then, we a number of times switched to a different project and went back, switched to a different project, went back. So we keep updated the pipelines and algorithms even now, but most of the work was done in 2018, 2019. As I said, we don't employ any linguists, so we knew we have to use machine learning to build some solution. We can't use any rules. We also knew that the current trend is to use RNNs, so we knew this is the way to do it properly. And we didn't have to care about any other baseline. We already have one. We had the Vader and we had the target, so we knew what accuracy we should achieve with the solution. The first model we built was very simple. The scheme is on the right side of the slide. It was very small, very fast neural network. You can see it has only 4 or 5 layers. And the input sequence it can process has up to 50 words. So we can process messages that has 50 words or less. It's okay. And we made some analysis and we found out that like 97% of all messages on social media have less than 50 words. So we can cover most of the messages easily. So that's the input. Regarding the input, the network can recognize and work with up to 100,000 words. I say up to, this is not fixed. We want every word we can process to appear at least 5 times in the training dataset, which can limit the number of words to something smaller than 100,000. For example, just 30,000 words. The reason to do this is that we don't want the network to overfit to specific word because it appeared just once with specific sentiment, for example. Another thing is the recurrent layer. We were thinking about LSTM, which is the most frequent way to do recurrency in networks, and GRU. And after some experiments, we found out that GRU works better for us. The performance regarding accuracy was equal between GRU and LSTM, but we are able to train with GRU multiple times faster than with LSTM. So we can train faster and predict faster and get equal results. So we decided for GRU. So that's the first recommendation or takeaway. Try GRU if you can. Another thing we were experimenting with are the embeddings. Just if you didn't work with text for some time, when we work with texts, with neural networks, we need to represent the words somehow. And typically we represent words with vectors. We use unique vectors for each vector, for each word. And like the most basic way to encode the words with vectors is to use one-hot encoding. And you have example on the right side of the slide, the upper table. These vectors consist of zeros and only one. And this way we can make the vectors unique for the words. Unfortunately, this means that the longer is the list of words we are going to process, the longer have to be the vectors. So in this case, when we have just 4 words we are going to recognize, we need vectors of length 4, because we need one place for the word and the zeros for other words. So if you would have a dictionary of 100,000 words, we would have a vector for each of the words that has length 100,000, which is very large, and it's not that fast to process such data. This is one of the reasons why word embeddings were created. Word embeddings are also word representations. They are also vectors. They are also unique for individual words, but it's basically a compression of the one-hot encoding vectors into much lower dimension. So in this case, again, on the right side, you can see that we use vectors of length 2 only. In reality, when you do this, the compression is much, much larger. It's like 200 or 300 of magnitudes. So you can reduce the amount of data that has to be processed significantly. During this compression, not just the vectors are shortened, but also some additional information is added into the vectors. It's typically some kind of semantic similarity of the words. So not just you have smaller representation of the words, but you have also some additional information encoded with the words. For example, if the words are fruit or sports, something like that. This process is time consuming. It needs a lot of data, and that's why people typically use pre-trained embeddings. They don't spend time training their own embeddings. Some examples are word-to-vec, glove, or some contextual embeddings. And when you want to use pre-trained embeddings, you have to be careful because, for example, in our case, because the architecture is so simple, a lot of weight of the model is right in the embedding layer. There's a lot of weights. So that part of the network does a lot of work. And to work properly, those embeddings have to be very well tuned to the task. And as I said, it may be tempting to use pre-trained embeddings, but it's not always true that similar words have similar vectors, because it always depends on how you define similar, in what sense they are similar. So what you can see on the right side of the slide is projection of these vectors for a lot of words. Here we used, in this experiment, word-to-vec embeddings trained on Google News dataset. We projected these vectors in 3 dimensions. We picked the word good, you can see it here. And then we looked for the most similar words to the word good. And we ended up with words great, bad, terrific, decent, nice, and so on. This may be okay for some tasks, but for sentiment analysis, this is not that good. You can see that word bad and good are, maybe they have similar use or context in sentences, but in case of sentiment analysis, it would break the performance, and did in experiments. So we decided to train our own embeddings for sentiment. It takes some time, but the network was small enough so we could do that. The benefit of doing it is not just better performance by default, but also that you can save some calculations in the embeddings, in the representation of words, some intermediate results, which means, in our case, for example, better separation of words by sentiment. And thanks to this, you can make the network smaller and better performing. You don't have to do all the calculations in the right time. In the time of prediction, you can do it during the training. An example for it is, again, on the right side of the slide. This is our set of embeddings. And you can see that for word, I don't know, hertz, you get only negative words, nothing else. I have even better example on this slide. Here we picked word embeddings for emojis, because we also work with emojis. And we projected them into 2 dimensions. And you can see the nice separation of negative emojis on the upper left corner and positive emojis in the upper right corner. And all neutral emojis are in the center and somewhere below this slide. So if you can, try to fit your embeddings to the task. I know it's tempting to use pre-trained embeddings, but try to make your own embeddings. You can make the network smaller, faster, lighter. Okay, so that's the basic architecture of the solution, or of the proof of concept. We didn't plan this to be the final solution, but it is. This is what we ended up using in production, until now. It's very simple and efficient. Most of the time, we spend playing with the data sets, because with such simple architecture, you need very good data and you need to have them in good shape. We first tried to find some public data sets, but it didn't work for us. In most cases, they were small, or they had just 2 classes instead of 3. They contained very long texts in contrast to social media, where we work with very short texts, or they were focused on specific domains like movie reviews, sports, and so on. So again, something we can't use very well for training of such network for social media. So we were thinking about building the data set, the training data set for us, somehow automatically. First, we were considering Amazon Mechanical Turk, but it's quite expensive service if you want to create a data set that has hundreds of thousands of texts. So we estimated the cost to $15,000 just for English training dataset. That's, again, a lot for such experiment. Another experiment could be with sentiment labels from our clients, because historically clients could sentiment the label manually in our product. Problem is that this data is very noisy, and it's also subjective. Every client considers positive something else. So it's unsuitable for general solution for all clients, for example, for Spanish. We also considered customer product reviews, but there's quite big difference between review sentiment and conversational sentiment. For example, typical positive phrases in case of reviews, product reviews, are phrases like quick delivery or 100% letter. If you use something like this in common conversation, it wouldn't be considered positive. And we also made some experiment with using emojis as labels, but this didn't work either. So we had to build a dataset in-house. It's the worst option. It's very time-consuming and expensive, but we didn't know about a better option than this. In fact, at least half of the time of the research team was invested into building some dataset. It wasn't building the network or training it. It was how to build a dataset to train the model. Luckily, we have a team of trained annotators. They are called taggers. And we asked them to tag for us 300,000 English messages. That's a lot of work. We prepared a manual for them and had a training session and handed over the manual to the taggers. We prepared the description of what sentiment analysis is, some references, we described the classes, gave them some examples, some also challenging cases and edge cases. We described them how to label the data, that it's more about feeling than rules, and that they don't have to label everything. If it's too hard to think about it and label it, skip it. We want more data, not more complex examples at the beginning. So they started to label the messages based on the manual. We let them to label approximately 400 Facebook messages. We measured their inter-annotator agreement. It was above 80%, which is good. So we asked them to not annotate the individual samples more than once or by one person. Typically, you have more annotators on one piece of text. We had only one of them and more texts because they agreed a lot in the team. Meanwhile, we created our own dataset, very stupid one. We used the Vader and other services to create labels just to have something to play with. And we trained the first network on this, and we made prediction on the benchmark dataset. And with this stupid training set, we achieved 75% accuracy on the dataset. We knew that that's not what we will see in production because the dataset was very simple. It wasn't challenging, but we had the first number. Then when annotators reached 15,000 hand-labeled messages, we wanted to check how well they do the labeling. We trained model on their data, and we got much worse results. we dropped with theoretically better data, hand label data, we dropped from 75 to 61% accuracy. We expected some changes, but we didn't expect such a huge drop. So we made some analysis. We found out that the labels provided by taggers are pretty well aligned. The team agreed in many cases. On the other hand, every time we didn't agree with their labels, we agree in our research team that those labels are wrong. So we had large agreement in taggers team, we had large agreement in research team, but low agreement between these two teams. So it's a good sign in some sense, because it means there's very likely some kind of systematic error. We prepared another meeting, another training, and we discussed what's going on. And after walking through many examples, we realized there's a huge, surprisingly fundamental misalignment on very high level understanding of what is sentiment. They had the manual, they had a lot of examples, but we didn't agree on what the sentiment itself is. For us, the research team, sentiment is how a reader feels when reading a text. For taggers, it was how the author feels when writing the text. It looks like not that important difference. If you write text like it's a nice weather, it's positive if you write it or if you read it. But there are many cases where this is not the case. And you can see such case at the bottom of the slide. For example, message, awesome deals for a hot summer. If I read it, I think it's positive. It's awesome, hot summer is great. But when taggers look at the text, they were like, it's an ad. And if you write an ad, you don't feel anything, it's neutral. So that was the huge difference in how they label the text and how we label the text, expected the text to be labeled. So they did nothing wrong. They just had different point of view on what is sentiment. So we need to A/B test this. We created some form with examples, labels from taggers, labels from us, and we let some, many employees to walk through that. And the outcome was that how reader feels is the preferred version of sentiment labels. So we updated the manual, taggers fixed the labels, and once they went to 20,000 messages, we made another check and we moved to 77% accuracy. So we fixed the problem, we could continue in the labeling, and that was it. Of course, after some time, we replaced the benchmark dataset, those 500 messages created by us, by the English dataset from taggers. And we used this dataset as a test set. Of course, the larger test set was the more hard examples we could find there. The accuracy slowly dropped to 70%. And we made some hard time to move back to 77 and higher. Of course, after some time, the product department wanted us to build models for more than just English. And in that case, we couldn't create the datasets in-house because we can speak English, we can speak Czech, maybe Spanish, but none of us can speak Japanese or Arabic. So we had to outsource the labeling. But we were in a situation when we already had very well debugged manual. So it was very easy to just hand over the manual, train the people, and let them do it the way we like it or we prefer. So there are three takeaways from this. First, double check annotations if you can, and not just once, do it in time, repeatedly. Second, if you want to update the manual or the way you label data, do A/B testing. Ask people if the change is good or not. And last thing, maintain the annotation manual. You never know when you will need it. I will skip this. Yeah, so we had some data. You already seen the architecture of the model. And of course, we need to train the model somehow on data. We use pretty standard training pipeline. We do some loading, splitting of the data sets. We pre-process the data sets pretty standard way. And we even train it pretty standard way. We just trained for only 20 epochs and 50 minutes because the network is very small. So even in cases when we have like hundreds of thousands of messages, we need just 50 minutes to train the model from scratch, which is great. We could make a lot of experiments pretty quickly. What you typically deal with is on the scheme at the bottom. Typically, when you work on a problem, for example, at school or some course, something like that, you have a clean data set. You have one large data set with labels. You take the data set, you split it into training set, validation set, and test set. You train on the training set and validation set. You do some evaluation during the process. And when the model is trained, you evaluate it once more against the test set. And you get the numbers. Problem is that in practice, this is not the case frequently because you don't have that large, nice, clean data set for training. Typically, you are able to build very small clean data set as a test set that's on the right side. And you have another one, much larger data set for training, but it's a dirty data set. The labels are not always correct. They are noisy, or the distribution of the labels is not the same, or properties of the text is not the same as in case of the clean data set. That's, for example, in situation when we have some small clean data set we created in the research team, for example, and this large dirty data set is a data set of sentiment from clients. They have different properties. Of course, when you train only on the clean set and then test on the clean set, that's the best case. You have the best data and you achieve the best performance typically. If you train on dirty data set and test on clean data set, the performance typically drops because of the misalignment between the two data sets. They are different, so you can't predict something you don't see in the dirty data set. Okay, so we were in that situation. We had some data, some third-party data, or our own data from users, for example, that didn't fit the distribution of the dataset from taggers, and we wanted to fix that. As I said, we created one large clean data set for English. We had 300,000 messages, but we were not able to create such big data sets for our other languages. So in case of other languages like Spanish or Portuguese, we were in this situation. We had very nice clean data set for tests and ugly dirty data set for training. And we are thinking about what to do with this situation. If you look at the images, the first picture is the dirty data set. And we are thinking about sentiment not as about 3 bins, like positive, neutral, negative, but rather a scale from negative through neutral to positive. That's much closer to how people evaluate sentiment. What this means, if you look at those pictures, the first one is one data set, for example, the dirty data set. Those circles are individual messages, and the black vertical lines are thresholds. There are thresholds between the sentiment. If you label just those 3 classes, you have to choose what is negative and what is not negative, and it's neutral, and then when to switch from neutral to positive. And you can have another data set. The data set has the same scale from neutral through from negative through neutral to positive, but the thresholds are placed differently. That's one thing we realized. Another thing is that when you let people label the sentiment, if the text is very negative, they label it as negative. It's very positive, they label it as positive. If it's something between negative and neutral, that's when they start to have a discussion if it's negative or not. So If you think about errors, about differences between data sets, for example, between the dirty and clean data set, the error or the differences are not uniformly distributed across the data set. They are focused in some specific places. You can see it in the red line at the bottom. Like, this is very likely, well, the data sets will not match each other. And if we train on the dirty data set, this is the place where we make most of the errors, not on the negative classes or extra positive cases, not on the typical neutral classes, but somewhere around here. So we thought that theoretically we could train the network on one data set because there is the scale of the sentiment, the same scale as in case of the clean set. The network can learn to solve the problem, not very well, but can learn something. And it can also learn the thresholds. And with the clean data set, we can fine tune the network, train it again on much smaller data set and just fix where these thresholds are. So we updated the pipeline with this. We start as usual, we have the dirty data set, we perform the training or pre-training and evaluation. Then we make the first measurement on the clean data set. This is the first number. And once we are done, we split the test set, we turn that into cross-validation set, and we fine-tune on these faults. We typically choose 3 or 5 faults. It depends on the size of the data set. But in this case, we have 3 faults. So we split it into 2/3, which we can use as a training set, and 1/3 we can use as a validation set. And we switch which blocks we use for training and for validation. We repeat this 3 times, calculate the average, and we do typical k-fold cross-validation. And just this trick helped us to bring the accuracy on average by 7% higher. Except in case of English, because that already worked very well. We had just the clean data set. So another takeaway, if you can, fine-tune your own pre-trained model. Like, pre-training and fine-tuning these are not techniques limited to the large third-party models like GPT-2 or ResNet. You can do your own small pre-trained model and fine-tune it to better data. So at the end, we had those hand-labeled data sets. We improved the training procedure, which helped us to reduce the cost. We didn't need 300,000 Spanish messages. We just did dirty data sets and, for example, 10,000 Spanish messages labeled in-house. It took us several months to collect the data. It takes a long time. And we created 10 dedicated models, one for every language that was important for us. So right now we are able to process with our models 10 different languages, and we have special model for each of the languages. All of those models, except Portuguese, are very closely reaching or even crossing the target accuracy we wanted to achieve, the 65%. And in the case of English, we even reached 79, which is just 1% below human level performance. Right now, we don't have any dedicated models for specific clients. Like, if we create very general Spanish model, it wouldn't perform as well if we create Spanish model for specific client, how the client does the sentiment or likes the sentiment. But that's simply how we do it right now. We don't have specific models for clients. We have just very general models for languages. So English works very well. One of those languages is even Czech. It's not that frequent to see Czech messages in the stream of messages we process. We just wanted to have our own model in language we understand. Of course, having models is not everything. You need to somehow apply those models on the data. So we created the very first processing pipeline. Thing we didn't discuss yet is language identification. If you create a model for prediction of sentiment for English texts, you need to somehow find out that the text is in English. So we needed to predict language of texts. We used PyCLD2, it's open source library. So we labeled the sentiment of the texts, we grouped those texts or those messages into batches by language, and then we just redirect the batches to the models. And with this approach, we were able to cover approximately 59% of the traffic of the whole company. What about the rest? What about the 41%? As I said, we have models for 10 languages, and we have some language detector. So there are just two reasons to not be able to assign a sentiment. First, we are not able to predict the language. So something is wrong with the language predictor or the message. And second, we are able to predict the language, but we don't have model for the language because we have just 10 languages or 10 models for languages. By the way, when I was talking about performance of the models, I was talking about accuracy. That's how we do it. We don't use precision recall. Every time we predict sentiment, we don't care about, let's say, confidence of the model. Every time we get a text, we predict sentiment. Why we don't have models for more than 10 languages? This is how languages are distributed in the stream of data we process. And you can see that it pretty quickly drops below 1% of the all traffic. So no, we don't want to build models for languages that cover just 0.1% of the traffic. And the long tail of the languages is very long. It's more than 100 different languages. The second problem was that we were not predict the language. And these are examples of messages where we didn't have the language. You can see that in some cases, they are pretty normal. Love it, loser, okay. They are normal English messages, but they are very short. And PyCLD was not able to predict language from these messages. In the other cases, again, you can predict language for this. You very likely can predict language for URLs. So after some time, we realized we need to do two additions or two modifications of the pipeline. First, we replaced PyCLD with fastText. fastText is language identification model from Facebook, and it has much better accuracy than PyCLD, or better performance. So we replaced the model. We have better prediction of languages. And the second change or addition was that we created a language agnostic model. This model doesn't need to predict language. It can work and it can assign sentiment on very specific texts. Basically, this model is just a set of some regular expressions and phrases. And it works such that if the text, for example, contains URL, we assign a neutral sentiment. If it contains just message, just mention, we assign neutral sentiment. If the message contains only emojis and those emojis are positive, we assign positive sentiment. So that's just another model. It's just not based on some neural networks. It's just a set of rules. Because it consists of mostly regular expressions, accuracy of such model is almost 100% if you don't make a mistake in the regular expression. And surprisingly, this model has larger coverage of the traffic than any other model we created except English. So the coverage is high with these simple rules. So with these two changes, we are able to move or to improve the coverage of the whole traffic from 59% to 82%. 10% was just thanks to the fastText, because fastText could identify a language in case of very, very short messages, which PyCLD couldn't do before. And second, 13% was added by the language agnostic model, just by identifying those emojis, hashtags, URLs, and assigning some predefined sentiment. So another takeaway if you can, identify and hard code obvious patterns. Like, it's no shame. I know it's very naive, but it's the last 10% or in every machine learning project. And we didn't stop with these. We were still thinking about those 100 and more languages in the long tail, what to do about that. We experimented with a multilingual BERT model. It was pre-trained, it was multilingual, it was able to process 104 different languages. And what we did was that we do this model, we fine-tuned the model with our English sentiment training set to train it to predict sentiment. And because it was multilingual, it was able to predict the sentiment also for other languages. So we used the large English data set and performed some kind of zero-shot learning for other languages. We validated the results of the model on the rest of the datasets we had on other languages, and the results were typically 60% accuracy and more. So it wasn't as good as our own models, but not that bad. And considering it's just a long tail of languages that has very small coverage, we just wanted to use it. So even though the BERT is much larger and slower in processing of messages than our model, thanks to the fact it can cover 100 or more languages, we were approved to use this in production. So thanks to this, we are able to even more increase the coverage of the traffic from 82% to 86%. So we got 4% coverage of the traffic with this BERT model. And that's all. That's end of the project, or that's the current state of the project. We created system for sentiment analysis for social media. We can analyze texts written in more than 100 different languages. We are able to process 50 to 150 million messages every day and cover 86% of them. We have some language agnostic model that covers a lot of text, like it's the second most covering model we have in the pipeline. We built 10 different RNNs for those languages we really care about. And in this case, we have accuracy 65, 70, 79%. We also use the BERT model, even though it's big and slow, because it can help us to cover the 100 plus languages. We don't care about that much. And we also made some experiments regarding the speed. So the internal models, those 10 models we built, they are 14 times smaller than BERT. They are 126 times faster on CPU than BERT. And right now, only 4 times faster than BERT on GPU. Reason why it's only 4 times is that the pre-processing of texts we do before we send the text into BERT, into the network, it's written in pure Python. It's not very efficient. So like 70% of the time is spent just with encoding the text before we send it into the network. And by the way, most of the time we really run the models on CPU. So in that case, it was really very large difference in efficiency. And that's all.
Okay, thank you very much. It was a fascinating talk. I would say that we have, I believe, more than 120 participants. That's our record. We have never seen so many people here, and I think it was like well deserved. It's really nice to see here somebody who can process 150 million messages per day. So before we will go to the questions, I would like to also thank you to our partners that support us even in this difficult year. Our partners are Resum, Seznam CZ, Konica SAS, and Datasyntics. You can see them on to the introduction slide or on our website. We would not be able to do what we are doing without them. And I think we can go to the questions. Marek, could I ask you to put the Slido on the screen. Thank you. So if you didn't yet ask, if you want to ask yet another question, go to the slido.com and put the code hashtag MLMU. And the first question is, how is the model implemented in production? Is it in Python or was it rewritten in other language?
Python. Right now, everything they do is in Python. And I think that's the reason why, for example, the pre-processing is so inefficient. It happened to us many times that we had some very simple Python functionality, right? Like just iterating through some fields and doing some small changes. And then we saw another version written in, for example, C++, and it was like 100 times faster or 1,000 times faster. Python is not a very fast language, but we use it. It's comfortable for the developers to use Python.
Like for me, it was like fascinating that you spent, was it 70% of time on the pre-processing? That's pretty crazy. The second question is, do you do any pre-processing for typos and classes of words that means the same thing, but they are written different on social media, e.g. lol, lul, slul, you know?
Yes and no. Like we try to avoid to do some really complex pre-processing because we want the network to do the job. But there are some cases, like exactly the lol with many O's, that's something we handle. We look at repeating characters. If they repeat more than 2 times, we reduce the number of repetitions to 2 times. That's one thing. Another thing is that we, for example, mask out URLs. It also helps with prediction of languages. If you have check text with, well, English URL, you can confuse the predictor. So URLs are masked, mentions are masked. We do this shortening of repeated characters, and we also try to, how to call it? We try to unify emojis. We, for example, if you use emojis, you can, for example, use different skin colors. So you have thumbs up in 10 different versions. What we do is that we remove the skin color from those emojis to have just one type of thumb.
Interesting. Never think of that. So the next question is about some well-known embeddings, like whether you did try the TF-IDF, fast text, or USC embeddings.
In case of this project, we didn't try TF-IDF. In case of other projects, I can recommend using TF-IDF. Sometimes it works even better than those contextual embeddings, even better than universal sentence encoder. Regarding the fast text, I'm not sure. Maybe we tried that, but right now we really use just tokenization into individual words, and we have our own embeddings. The problem with the other embeddings is that we would have to retrain them anyway. Like we can use the original embedding and then retrain it with what we need for the sentiment.
Okay, thank you. The next question is, if I remember correctly, a language can have over 350,000 different words. So how does your model deal with the words that don't fit into the selected 100K set?
We ignore them. Yeah. Why it still works? It's true that we have, like maybe we have even more. We have, I guess, maybe a million different words, for example, in Czech. But they are very, very rare words. And in most cases, when you talk about something that's positive, negative, neutral, you typically use some standard words like that you are happy. Yes. So if the word is so rare that it doesn't appear in the first 100,000 words, it's also very, very rare in the datasets.
Okay, thank you. The next question is, what was the class distribution of your total data set? The question is what is meant by total data set here, but yeah.
By the class distribution, you mean the share of positive, neutral, negative?
Yeah, I guess that means like how many percent were positive, negative, and neutral.
During training and tests, we always use balanced data sets. So it's 30%, 30%, 30%. We did our best to train the models such that they perform equally good in all classes. That's why we balance it. And in production, the share is, I think, 20-25% positive, 20 or 25% negative, and the rest is neutral. So we have twice more data that's neutral than those that are positive and negative.
Okay, thank you. The next question I'm also interested in, like, do you retrain your model? Do you do it periodically?
No, we don't. We think that our understanding of what's positive or negative doesn't change in time that much. So we don't need to retrain it frequently.
The next question is from Katarzyna Weslowska that used to have a very nice talk here last year. Wouldn't it be easier to annotate whatever positive, negative expressions you find in the data instead of taking the author-reader stand's overall impression?
I'm not sure if I understand this question. Like,
yeah, I'm also not. Honestly.
Like if we could, for example, build a dictionary of positive and negative expressions and look for them in the data and use it as labels for the text.
Maybe.
If this is the question, the problem would be that we would overfit those phrases very likely.
Yeah.
It's close to the approach we tried with emojis. We have a lot of texts from social media. You can see a lot of emojis in the text, and you can use the emoji as a label, for example. If there's a happy emoji, it's very likely the text is positive. Problem is that the emoji is integral part of the message. So you can leave the emojis in the training and test data, use it only as a label and leave the emojis in there. In that case, the network will overfit those emojis. It will predict sentiment based on emojis, not the rest of the text. Or you can use the emoji as a label and then remove the emoji from the text and train on the text only. In that case, it may happen that you, by removing the emoji, will change the sentiment of the text. So if we understand the question correctly, I hope this will be the answer.
Maybe we can answer it later in the breakout rooms during the small group discussion. Something I'm also interested in is the next question. When you do those 70% of preprocessing, like constructing of the embeddings, do you always encode the whole words, even for the languages that are not English, or do you break them into pieces, like sentence piece or word piece? Or
we use whole words. We were already thinking about experimenting with subwords, but we didn't try it yet.
Okay, interesting. So even for the Czech, you are using the whole words?
Yes. Yes.
Okay, thanks. Would you consider culture difference to play a significant or any role in understanding what is meant by sentiment?
I personally didn't have to consider this, but I hope that those annotators did it. Yeah, so it's not that Czech person was annotating Portuguese text. When we outsourced the labeling, we hope that those who are doing it understand Portuguese well enough to understand the differences and were able to detect the sentiment properly.
It should be like easy to check if you look for the annotator, how many % of the annotated sentences are positive. Then if there are the culture differences, you should see like, you know, the Czech person see 10% thinks as a positive and US person like 80% as a positive.
Yeah,
I don't know.
We did this analysis. I think that the data analysis team who were working on the Game of Thrones analysis, they were also doing this analysis, and we found, let's say, significant differences in amount of positive, negative, neutral messages between languages, between countries.
Interesting.
But it's a question if it's error on our side, we have wrong labels, or if it's fact that, for example, Spanish people are more positive and happy than us.
Okay, thank you. Have you applied transfer learning on embedding training? I think it was answered at the end of the talk, but anyway, adjusting weights in the embedding layer during training phase of the network.
It's definitely doable. We just didn't do that. We trained our own embeddings from scratch.
Okay, the next question, we are going in the direction from the like most favorited question to the least favorite, so we might like speed up a bit. What metrics did you use to calculate model performance?
Accuracy.
Okay, accuracy, not like entropy or something.
Accuracy, and we didn't, as I said, we didn't even use precision and recall. We didn't want to have some threshold saying the network is confident enough. We wanted everything that's given to the network to be processed and labeled. So we label everything we get, and in that case, we used accuracy.
What does model do if included emoji sentiment is different than the of the text of the message? For example, because of sarcasm.
I don't know. It's a neural network, so I have no idea. For us, emojis are tokens as any other word. The network, I think, doesn't see difference between word happy and happy emoji, or maybe there is difference, but it treats them as words. They are equal things.
Okay. How important is the order of the words in the message? In our experiments, we found that models based on order are not worth the performance against BOW. I'm not sure what that stands for.
I think that the model definitely cares about order. It also understands inversion of sentiment. If it's beautiful or not beautiful, it turns the positive to neutral. And we tested this. And we did another thing. If you have sentence, maybe I will recall it. My notebook was broken, but it is working now. And my notebook was working, but it is broken now. The second sentence is negative, the first one is neutral. So we tested it, and there is difference in the order, or the order changes the sentiment.
Okay, maybe I can ask some follow-up question, but usually if you like really try to play with some irony and something, it's usually easy to trick the model, isn't it? At least when I train my sentiment analysis model, then it's like, you know, it gets it like in most of the cases. But if you take the sentence is like, this is the best movie I cannot say, or something like that. It's usually.
Yeah, of course, if it's complicated, and specifically in case of sarcasm, it's in these cases.
The next question, did you had to make some language-specific modifications to your model?
We were playing, in case of Arabic, we were playing with order of the tokens in the sentence. But at the end, we didn't have to apply this change. I think that we don't do anything special. Well, we are lucky because right now most of the languages use Latin characters. I think that once we will try to work with Chinese or Japanese, we will have serious problems with the text.
Thank you. How do you import the data? Do you use Azure? I guess you have your own. Sorry.
We typically use, or we typically store data on S3, and we use, we train, specifically in this case, we train the model on Apache Spark in Databricks and stored all data on S3 and load the data from there.
Next question for Katarina Wysłowska. How about aspect-based sentiment analysis? I love their tacos, but the pizza sucks. Is it positive or negative? That's a good question. I like it.
Yeah. We can't do this right now, but like our manager of the innovations team, he loves aspect-based sentiment, and he just waits to have enough priority for this program to look at it. So we can't do it right now, but we are looking forward.
Mhm. Oh, the next question is, what about messages that contain several languages mixed in together? Can you separate different parts of the language identifier? Can you separate different parts, or is the language identifier unable to identify them?
We can't do it right now. We can't.
Yeah,
So if we make,
that's really hard.
we just, I think, pick the most, like the largest part of the text, I guess, and then the network like analyzes the largest part of the text. A good thing about this approach is that the words, the network, for example, for English language, is able to process. Those words are English words. So if the text contains some Czech words, the network just ignores them.
Mm-hmm. Okay, the next question, why did you choose machine learning instead of the linguists? I'm not sure that there's
We
anything to say.
don't employ linguists.
Okay, next one.
We are thinking about hiring someone. Like
Oh,
we,
nice.
we run into many issues in different projects where we are like, oh Jesus, is there anyone who understands, for example, how words are separated in Japanese, Korean, Chinese? How can you know if these are specific words or just some prefixes? So we are thinking about at least becoming a friend with some linguists.
Mm-hmm. Okay, maybe some linguists listen to us and can follow. Do you average predictions of, oh, sorry, change of the order. So what's the next? Okay. Do you average prediction of k-folds model, or how does it help to improve the accuracy? I'm not sure that I understand the question.
What we do is that we split the set into the k-folds. We do it 3 times, then or 5 times, 7 times, we remove the best and worst result and calculate the average. This is some, let's say, guess of how well it works after this fine tuning. And then when this is done, we train the model once more on the whole data set, on all the folds. So the measurement is just a hint to how well it works after the final fine tuning of the training.
Mm-hmm. So the next question.
And how does it help to improve accuracy? Yeah, because when you train on the dirty data set, you get worse performance than is possible with clean data set, with good data. So to describe it like very high level, on the dirty data set, the network can learn to understand English, but not very well to understand sentiment, or at least not precisely because the labels are noisy. And with the fine-tuning dataset, which is very small, we just retrain it. It already understands English, so now it can focus on the sentiment itself and improve on the sentiment.
Thank you. The next question is, why is Spanish model twice bigger than English one? Is it more complex?
Yeah, I was this as well, because typically the models have just 30, 50 megabytes. The Spanish model has almost 100 megabytes. And the largest part of the model is the dictionary of the words it can recognize. So my guess, there's absolutely no difference in the architecture. So my guess is that the difference is in the embedding layer or in the dictionary of the words. So very likely the Spanish model uses all 100,000 words it can have in the dictionary.
Interesting. So does your Spanish language take into account region differences? There are some pretty wild differences between Spanish-speaking countries. That's a good question.
Nice, like very good question, because we currently have problems with clients from Brazil. And they are also telling us that there are huge differences in meaning of specific words and phrases and so on. Unfortunately, we don't have specialized Brazil data set and specialized like 10 different Portuguese data sets, 10 different Spanish data sets. We don't have enough data for this. So we have only one general model for, let's say, average understanding of sentiment in Spanish and Portuguese and so on.
Okay, then we have like the same question twice. Could you train a model collectively with all the languages together?
I think theoretically we could. Like there are models that are able to process multiple languages. In our case, we think that the benefit of having those models like having separate models for individual languages is that if we know that number of messages for English is, or amount of messages for English is 10 times larger than for Spanish, we can deploy 10 English models in production and just one Spanish model in production. We can save resources. We can focus on what amount of resources that specific model or language needs. Another thing is that every time we, for example, need to retrain the Spanish analysis or Spanish sentiment, we don't need to retrain or check changes in accuracies for other languages. They are completely separate models.
Okay, then the next question is, you have mentioned that available annotated texts are small. Are you contributing back to the community and trying to improve the situation? Do you have a public data set?
We are contributing, but not with the data. Very sorry, but this is how we make money on it. Right? We can share data set, and our competitors would have sentiment next day. So we can't do this. What we do, we write some text. We also have some meetups, so we at least try to share our experience. And sometimes when we have some interesting implementation, for example, of some text processing, we share it.
Thank you. I believe like if somebody want to try, like if you want, you usually can find some sentiment data sets for the given language. Like I remember myself looking for them just for the movie reviews data set that's publicly available.
Yeah.
Did you try to combine all models using some ensemble method? Do you get the better result that way?
We didn't do ensembles. We didn't do ensembles. We really wanted to have lightweight solution. Problem of ensembles is that they consume a lot of resources. So it would turn the model or the prediction 5 times, 10 times slower. We didn't want this. So we use only this one very lightweight model or architecture.
The next question is, if you consider emojis in the text as a lead identifier, what about misplaced emojis? E.g., people sometimes mistakenly send like the throwing face instead of smiling face.
We do nothing about this. They simply send unhappy emoji and we have no idea why. So we analyze it as if this was intended.
Thank you. How long were you training your embeddings? What method did you use to train them? If you can say, of course.
I think I can. It's part of the architecture. We use embedding layer in the architecture, so it's trained at the same time as the rest of the model. And there's nothing special about it.
Yeah.
No.
I'm not sure. Did you mention which architecture do you use? Do you use TensorFlow or PyTorch? Just for the curiosity.
Yeah, right now we use Keras, which is just
Keras,
around.
TensorFlow. Okay. So embedding is always 2D vector. I'm not sure what this question really means. So this is like last few was like 0 like, so we can just, if you want to answer, then you can.
Embeddings are typically very high dimensional vectors. The most frequent dimensions are 100, 250, or 300 dimensions. What I showed you was 2-dimensional, simply to make it simple and readable for people.
Thank you. Now we thank everybody for the question, but we are already like answering them for some time, so we will go through it a bit faster. What targets have you used for the analysis? I got negative, positive, neutral. Another type, which team the message should go to? I'm not sure what that means. Was which team the message should go to, yeah. Yeah, I don't know either. Maybe we can skip that one or answer it later. The next one, have you done analysis of the dataset size? If you have twice more data, do you have any idea whether it would significantly improve the model? That's a good one.
Yes, we did. And we didn't do it at the beginning. We did it at the, like, in the phase when we already were doing the fine-tuning. So thanks to the fine-tuning, we reduced the amount significantly. And then we made the analysis how much data we need to, let's say, so what's the amount of data when the improvement in accuracy will stop growing, let's say. And it depends on the language, but we ended up with numbers like 10,000 messages. So 4,000, 5,000 is enough to have almost the best result possible. And 10,000 was like the optimum.
Okay, the next question is, did you consider using active learning?
No.
Yeah. You know, it's not totally unreasonable. What was the reason for not considering metrics such as precision recall? You kind of answered it already.
Yeah, we did.
So
because when you use precision recall, you consider that there's some threshold of confidence when, if the model has lower confidence than threshold, you don't provide prediction. That's not our case. We always provide prediction. That's why we use accuracy.
Would it make any sense to work only with 2 labels, positive and negative? I think that's something what you use pretty often when you look for some, you know, tutorial on TensorFlow. They usually only work with positive and negative labels.
Yes, we wanted to have 3 levels. So from the very beginning, that's why we use 3 levels. We also experimented with 2 levels. If you use just 2 classes, if you use just 2 classes, you can achieve much better results. We had the data sets of some, I don't know, reviews, I guess reviews with stars. There were 5 stars. And we translated these stars into 3 classes or 2 classes. So we could have the same data set and have 2 or 3 classes for the sentiment. When we were training to predict the 3 classes, we achieved like 71, 75% accuracy, 73% accuracy, I guess. And when we trained for 2 classes, we achieved 92% accuracy. So just having lower number of classes, it's easier to make the prediction, or you can achieve better results. But we wanted to have 3 classes.
Oh, interesting. I remember that my classifier achieved 95.5% accuracy. So it really probably matters on the data set that you use. Like but definitely if you use just 2 classes, it's easier. The last question, not really a question, but a note from Katerina Veselovska. 10K fake Facebook post manually annotated. So if anybody is interested, take the print screen, because I unfortunately cannot copy that into.
I will take the screenshot. Just question to this. How about licensing? Like, can we use this commercial space or not?
It seems to be academic data sets, so there's at least a chance that you can, but maybe you can ask Katarina or people from, I'm not sure what's the deal in that, but otherwise it's a faculty of mathematics and physics at the Charles University, so maybe. Okay, thank you for spending time answering all the questions. I hope that it was useful for the people. And maybe you can give a few minutes like the bathroom break for everybody to get focused. And we will continue with the final part when we will split all the people that are here. I can see that it's still 37, 36 of us. And we will then appear in a separate room. So we will not like discussing all together, because 36 people discussing in one room would be too much. But we would be like, I believe, 5 to 8 people in one room, and like you can chat about everybody, about anything. You can chat in Czech or Slovak if you want, but before you do so, like make sure that like everybody in the room like understand Czech or Slovak. Okay, so let's wait 2 more minutes. So it's 7:35, so 7:38, we will move to the break rooms. And thanks everybody for coming and asking all the questions. Sorry if we didn't understand some of them. And definitely thank you for spending the evening with us.
Yeah, thank you.